Thank you very much, and I want to thank everyone for joining us today. So it's my great pleasure to introduce Dr. Tirathorn Kadithum, if I pronounce the last name properly, or in short, Min, as he prefers to be called. So Min earned his bachelor's degree in mechanical engineering from Chulalongkorn University in Thailand in 2007. And then he obtained his master's degree in chemical engineering from University of Calgary in Canada in 2016, and got his PhD in applied mathematics and computer science from the Technical University of Denmark in 2020. So I think he went around the world to earn the PhD degree and all the degrees that he has achieved so far. Following his PhD, he was postdoctoral researcher in mechanical engineering and mechanical and aerospace engineering at Cornell University from 2020 to 2021. And then he joined the Sandia National Lab as a senior technical staff in the Climate Change Security Center laboratory in New Mexico. So Min has authored over 25 research articles, and his research interest is mostly focused on machine learning, advanced finite element approximations, and model order reduction, particularly in the context of parameterized nonlinear partial differential equations. Without further ado, I'll hand over the stage to Min, and we're all very excited to listen to your presentation.
Cool, thank you. Let me share the screen. Whoop. Up here. Oh, cool. Well, why is on the other screen? Can I move it? Okay, let's go with this. But yeah, thank you for for introducing, and yeah, great pleasure to be here. I just want sorry, just try to move the thing. It just doesn't. Can already see. But just leave it here, I guess. Yeah, no, but haven't used Zoom for a while too. Okay, because yep, and yeah, today we're going to talk about our work that we've been working on since like 2021, and the goal of the talk is just try to, like machine learning nowadays is very popular, right? But can we actually use ML any shape or form to approximate physics? And at least there are three main ways that I'm looking at right now is data-driven, physics-informed, and the most important thing I think moving forward is actually physics discovery. And also want to thank all the collaborators listed here for the work that we've been doing together for the past couple of years. And yep. So for the outline of this talk, I will start with data-driven approach. So anything that's kind of like given data or parameters and want to predict state variable that we desired, or a physics informed. So instead of using purely data, sometimes we can use governing equations in terms of ODE or PDE to teach the machine learning model. And lastly, because sometimes we already have all the governing equations, right, to describe all the complex system that we have, sometimes we need to actually discover the underlying physics. And what we're talking here, not like doesn't need to be the Darcy equation or Navier-Stokes or any known equations, right? We also can think of it as an effective equations that describe our system at the scale of interest. But yeah, so want to make sure that we get all the the term like alive. So we here talking about parameterized system. So what I mean by parameterized system, right? So let's say we have a system that take the input as a parameters, and then we want to learn more or to understand the quantities that we interest. So let's say in our application, right, of CO2 storage, parameters can be like material properties of the rock itself, conductivity, porosity, heat transfer coefficients. And the quantity of interest can be like, CO2 saturation, fluid pressure, stress, tensor that will cause earthquake, or it can be temperature of the fluid itself. And this system, right, can be technically represented by two ways. The first one is empirical model. So, think of it as a regression models. So we have, data of parameters that map to quantity of interest, and then we try to build a regression model using parameters as a independent variable and quantity of interest as a dependent variables. And the other way around, right, is to use, governing equations that discovered by, let's say, first principle approach, and then we have governing equations such as Darcy, Navier-Stokes, Biot's equation or Biot equations, so on and so forth. But also want to emphasize that sometimes the system is too complex, right? We not only have the governing equations that can correctly describe it at all the scale. So sometimes we just need to discover it at the scale that we interest in. And I will start with the concept of data-driven model itself. So, there are many variations, right? I just try to summarize down to, to what I think is essential in nowadays data-driven model. So given parameters, right, which can be low dimensional or high dimensional, we want to be able to predict state variable, which typically is a high dimensional data. So one can also try to map low dimensional parameters, right, to the high dimensional state variable itself, but it would be pretty hard. So typical approach that we would do is, let's say we given a snapshot of state variable itself, one can do manifold learning or data compression in general, and it can be linear or non-linear compression. And the example of linear compression would be proper orthogonal decomposition or POD, and non-linear compression can be anything like autoencoder based model. And once we get, we condense into a reduced manifold or the dimension that, much lower than the state variable itself. Now the second step is to do parameter mapping, which means you try to link the parameters of interest to the low dimensional manifold. And the goal is, with the given parameters, what is the low dimensional manifold, and then you reconstruct the lower dimensional manifold into the state variable that you decide. So that would be a quick summary of the data-driven model, at least from what I'm working on. So now talking about pros and cons of this data-driven model, right? So for me, it's like a boilerplate template. So once you, let's say, develop it for a CO2 storage model, you can just use the same model with some, fine tuning or some tweak for a geothermal model. So it's very quick turnaround in the real world setting. And at Sandia, right, we've been successfully to just, move our template around among all the subsurface, like application ranging from like oil and gas to geothermal to CO2 storage without a lot of effort to actually, fine tune the model itself. So make it very quick turnaround. But these data-driven model also come with a lot of cons, right? The first one is data hungry. So without a massive, amount of data, the model is actually not accurate enough to predict in the real world setting. And also it's lack of robustness. So think of it like, let's say you have a parameters in the range of 0 to 1, and then while you deploying your data-driven model, right, the parameters shoot off to 1.5. Now your prediction is not reliable or robust anymore. So now you have to retrain your model again and start the process all over again, which is actually not cheap in terms of computational expense. And the last one, which is very important nowadays, is the explainability. So by treating the the data-driven model as a series of neural network, right, or a black box, it's just very hard to understand why the prediction sometimes good, sometimes bad. So a lot of work has to be focused on the explainability part here. And there are a bunch, right, of data-driven reduced order model nowadays. But what I want to lightly dive deep today is what we call operator learning. So one can think of typical neural networks as a points or vectors to points mapping. So given a set of points or parameters, neural network act as a nonlinear transformation that transform those parameters into the state variable that you desire. But there is a new way of thinking, right? So operator learning kind of suggests that we're not going to do points to points mapping anymore, but more on functions to functions mapping. And why functions to functions mapping is better, right? The first reason is it's a mesh independent. So let's say you train your model based on your finite element mesh, with a fixed topology, but now you want to know the coarsening of your solution or finer resolution. Now you have to retrain your model again, right? But by learning functions to function mapping, you can go from phi to cos and go back from cos to phi without any additional interpolation step. And also the second reason, which actually might be more important, is by learning functions to function mapping, you speculated that the model will be more generalizable, and there are a wide varieties of these like operator learning model, but I would think of them that just stem from two main branches, and the first branch is the FNO or Fourier neural operators. And the second branch is a deep operator learning or deep honest. And I think the main difference of the classical form, right? Because nowadays they kind of fuse together, but in the classical form, the main difference is the FNO, kind of try to map topology or your mesh in combination of your parameters using one neural network. But DeepOnet kind of doing it differently. So they decompose the topology part, or what they call a trunk net, and the parameters part into n finite neural network. And what we're going to talk more today is actually based on the deep operator learning, not the FNO part. And this is actually the work that we published this year. We developed a neural operators based on deep neural operator approach or deep ONET. And it has been successfully used in the large scale CO2 storage in Illinois. And the main components are, there are three main components. And I want to emphasize that, our parameters, right, can be, permeability, porosity, injection rate, time, and spatial coordinate. And what we actually want to map to are fluid pressure and fluid saturation. And based on, deep O-net school of thought, right, we decompose our embedders into three parts. The first part, what we call homogeneous parameter embedder would take care of any, lower dimensional input here, such as injection rate. And the second part would be heterogeneous parameter embedder would take care any, high dimensional input. Here is conductivities and porosity. And the last one would take care of topology, which here is temporal and also spatial coordinates. And all these embedded jobs, is to condense the parameter space and also the topology space into a reduced manifold before we project it back to the quantity of interest that we desire. And what I believe, right, that this model is actually pretty cool is that our data set or our snapshot composed of like, a thousand upon thousand realization of these conductivity fields. And for each realization, there are 1,000 timestamp. And for each timestamp, there are about 2 million degrees of freedom within the computational domain. So if you stack all those up together, right, we have like billions degree of freedom to learn from. And technically you can use all of, the full computational domain as your input, but you also need like a huge computational resource, right, to utilize to be able to learn all the mapping. But what we did here is different. Instead of like using the whole computational domain as an input, we resample, the computational domain at each back propagation. And why do you think that worked, right? So think back of like statistic, 101 back in the when I was in bachelor degree. So it's the more you sample, like the more time you sample on the right hand on the row here, or the bigger sample size, finally, the sample estimate will reach to the population mean itself, right? So the thought that we have at that time is like, if we do many samples throughout the training process, finally we will reach the actual embedding of, the population. And let's put it into a test. So, oh yeah, this is actually a wrong title here. We're not talking about graph right now. But so what you can see here is the moving average of validation loss, not the training loss itself. And we use different sample size ranging from 100 to 100,000. And you can see, right, using 100 sample per back propagation, it is very small, right, compared to 2 million degree of freedom that we have. So yeah, the accuracy is not great, but the accuracy keeps improving as we increase the sample size. And by the time we reach 5,000, it's, kind of saturated and it's very comparable to 100,000 sample here. And I want to emphasize that the wall time, train for 100,000 sample is actually 8 folds larger compared to the 5,000. So we can achieve something with the same accuracy in a much cheaper cost. And yeah, to summarize, the model that we publish here is that, we can train with a fraction of computational domain, right? 1.8 million spatial coordinates, but we use only 5K of it, and it's still the same accuracy. It's also super flexible. It can infer at any degree of freedom, ranging from 1 to 1.8 or even more if you like. And those coordinates during the prediction phase do not need to exist in the training. So you can go, very high resolution or low resolution up to your desired. And the model is super lightweight, right? It's only 1.7 million, trainable parameters compared to like LLM nowadays that's, in the billion or trillion parameters. So yeah, it's almost nothing. And yeah, we actually tested on the CO2 storage project in Illinois based on the SMART initiative here. And with this, right, we already happy enough to like, the model is pretty accurate, it's pretty cheap, but we still think that we can do it better. So in our classic model, right, in the published model, each block of embedder is represented by a series of, linear layer and activation functions. Our thought, right now is that can we switch off the linear blocks, right, and then replace it with the graph? Can be graph convolutional or graph attention itself. So our thought is like when we sample one point, right, not only we aggregate the data of the point itself, we also want to aggregate the neighbors that we show on the left-hand side here of the data itself. So it would be able to convert much faster than our typical neural operator that we just did. And yeah, the rest of the model is still the same. We only test to the heterogeneous parameter embedder part. So we switch out the linear block and then replace it with the graph block. And yep, the result is as follow. So again, it's the validation loss, and the blue one is a baseline model from we published this year. And with the graph convolutional and graph attention, one can see that the accuracy improved significantly. And the trainable parameter reduced from 1.7 million to only 700,000. So cut by about 60%. Yeah, so the key takeaway is, data driven is it's pretty easy to build, right? Like you can build it for one application and then use it as a template, and can adapt to any finite application that you desire. And it's very easy to, integrate the physics informed laws to the model by just, adding the additional laws to the end of your training. But it also lack of explainability, with something we need to work on. And now we move on to the physics informed ML, which the concept here, I know there's a wide range of variation of physics informed, but I try to condense it down to, to a digestible concept here. So at least for me, there are three main parts. The parameters, which can be topic of material properties, initial conditions, or boundary condition itself, combined with any differentiable model, right? That can be neural network in this part, and then combined with differentiable rules. So, any partial differential equations, let's say, you can train your physics informed ML. And I think the most special part of the physics informed ML is it's not only about forward, right? The model can do forward paths. So, given material properties and the model and the rules, we try to train, the model, but it also can do the inverse part, which means with a mismatch between, the state variable that you have, you can also not only update your model itself, but you can update your material properties. So it's not like typical, data-driven model, right? It's work in forward and inverse path simultaneously. And I think this is a very strong point for the physics informed ML. And the pros and the cons of the physics informed ML. And start with the pro first. So yeah, definitely less data hungry, right? Because we technically give the model more information in the form of partial differential equations. And it's also very robust. And I want to emphasize here that once it's trained, because at least from our experience here at the lab and our collaborators too, it's very hard to actually train the model. The training stability is one of the downside for sure. And it's very explainable, right? Because we actually give them the rules to learn from. So we know exactly what are the rules that we give them. But with all these benefits, it also come with the cons. And the main three disadvantages here are, it's very hard to train. The training stability is one of the main constraint here. And it's also super expensive. Like to train like a toy problem, right? Of like Poisson equation or Burger's equation, it still take a very long time, right? And if one want to use in the real scale of, let's say, CO2 storage, it's turned into a very, very expensive operation. And it's still not straightforward to handle high dimensional input. So there's a, you know, attempt like such as the one from Brown, right? The X-pin that try to handle by breaking down the domain into subdomain and try to link all the subdomain together. But at the end of the day, it's still not straightforward to handle a super high dimensional input, right? Imagine each degree of freedom in your domain represent different material properties. It's just not possible to break down into like one subdomain, one degree of freedom. And yeah, so I want to dive deep into the the model that we've been developed back in 2021 to 2023. So this model was start off as a data-driven model. And then we're thinking about like, could we do it better, right? Extend it into physics-informed model. So the data-driven model part is, think of it as a unit model with the given, certain boundary conditions and source term. We want to map it into a state variable like pressure, saturation, so on and so forth. But the physics-informed part is here. So the last layer of the output, instead of only predicting the state variable itself, right, we apply the finite difference stencil to calculate, the residue itself. And what I want to also emphasize here is that it's not the typical, physics-informed ML, right, that enforce the residue loss as a strong form, but it actually enforce the residue loss as the integral form or the weak form itself. And we'll show in the result that, it actually works much better than the strong form. And also, yeah, in the output, it's not only the output of state variable, right? We also want to do pointwise loss or enforce the loss of the boundary condition itself, and so on. And yeah, this is one of the example that two main gist of this model. The first one is how we create the finite difference stencil. So the model itself based on convolutional neural network. So technically what we did is we just create a filter of the last layer that represent the finite difference stencil. So let's say, del U by del X here just approximates by, first order finite difference and then applied as a filter of the convolutional layer as follow. And the same goes for Y and, second order derivative, so on and so forth. But also what is kind of pretty unique here back in the day is that instead of like typical pin, right, you actually do soft constraint for boundary conditions. So technically you give your boundary conditions as an input, and then you ask model to predict your boundary conditions, and you adjust your neural network based on the mismatch between the actual boundary conditions and the predicted boundary conditions. So at the end of the day, it's like a soft enforcement, right? If you want to think of the finite element model. But what we did here is we actually using padding to actually enforce the hard boundary condition for BC, which also actually help a lot with the training itself. And yeah, so jump into the result, right? So we have two results, the training and the testing. And the black line here is our proposed model with the weak form, and the blue line is the proposed model with a strong form. And the CNN here is just typical data-driven model. So as you can see here, one of the case that we show in the paper is that using strong form, the model is actually very struggle to train and perform pretty bad in the testing too. Even worse than the data-driven itself. That kind of surprised us. But yeah, by using the weak form to enforce the loss itself, the model actually trained much better, like the black line here. And also it's getting much better in the training set too. Hey, the testing set, sorry. And yeah, the key takeaway is like one can always compensate data, right, with physical rules. And that actually help the model to, regulate itself much better. And weak form loss, different than the classic physics informed, right, which is in the strong form, may achieve a better performance. And it's also possible, to enforce the BC and IC, like using hard enforcement instead of the soft enforcement that PIN normally does. And now moving on to the last part of the talk here, which is actually not the work that it's actually the work that we plan to do next year, but I think it's one of the coolest thing to be a part of for next year, is that back into the parameterized system, right? Given parameters, we have a system that will, map to the quantity of interest. Assuming that we don't know what is that system, right? And we want to actually not represent it by a regression or empirical model, but we kind of want to find the physics or underlying rules that govern this system itself. Typical way, right? One can do sparse regression, or symbolic optimization. And I think the main difference just boiled down to symbolic optimization is based on the tree-based approach. So it can grow into, infinite number of form if you have time to search it. But for the sparse regression, it's limited by the vocabulary, think of it as a vocabulary. The vocabs that you give the model, and the model just try to reduce into, the simplest form using sparse regression. And why we very invested and interested in this kind of model is that back into our domain, right? We want to inject CO2 back into subsurface. And this subsurface, composed of many, like million of fractures, but I put the line here at fractures and just to represent that there are many of them. And if you inject your CO2 too fast, right, because you want to keep CO2 back there as much as possible, it can create an earthquake. So one can also, try to model each fracture to predict the earthquake. But it's not possible, right, to model millions of them at a time. It's just too computationally expensive. So what we want to develop is the effective governing equations to predict that when the earthquake going to happen, given the CO2 injection rate. But we also don't want to do it in the data-driven fashion because we not understand, the system itself, but we want to do it in the explainable fashion so that we can learn something from our mistake, right? Not just to predict something. And, the whole idea is like this, like, let's say given we have different modes of measurement, the red one can be any satellite data, right? Let's say, SAR or INSAR, and V is like a surface measurement, which can be like an impedance or any geophysical measurements. And the green is a system that we actually want to estimate. And we only have a very sparse measurement, right, as as a well here that we drill into the subsurface. And this, system is represented by parameters mu and state variable s. Typical like physics discovery approach, one can only use, mu to find the governing equation of s. But what we are doing here is different. So instead of using one modalities of data, we will use, let's say here 3 different modalities of data. And the whole idea is, the same thing. We try to condense it into the vector or embedded representation. And instead of, doing the physics discovery in the high dimensional data itself, we will do the physics discovery based on the reduced dimension or reduced manifold. And because a symbolic optimization, right, can produce infinite number of, governing equations, so it would be almost intractable, right, to reach the, the global optimum, mainly just, stuck in the local minimum. So our proposal actually focus on like, can we actually create, the accumulation of database of all the physics that we discovered before, and now we can do like a lookup, and propose the term that should be in the governing equations. And yeah, just to explain, right? Let's say, a part of the discovery here is a tree of, some term of, a differentiable terms, and also composed of, 3 modes of data. And by doing this, not only we discover the, the term itself, we also want to discover the coefficients that associate with each term. And we don't want to do only the forward equation, right? We also want to do the inverse equation simultaneously, like what pin normally does. So not only given the mu and the rho and the v, we want to predict state variable. We also want to reconstruct our parameter space mu given s, state variable, rho, and mu. So different modalities here. And yep, and also, the stretch goal here, right, is not only we want to do only the measurement or one modalities of data, right? We also want to be able to understand the different modalities of data. So assuming the step number 1 here, right? We have a state variable that, s and parameters mu that created by any high fidelity solver. And we know, right, this high fidelity solver is governed by the state Darcy equation. So we technically have a ground truth to train the model. And then the byproduct of the training is actually the embedded, or the manifold here that we want to identify. So now once we know that, Darcy equation is represented by this set of embedded manifold, right, we can technically train the model to learn a different modalities. So let's say a text of Darcy equation or the photos of, Darcy equation should actually yield into approximately the same embedded manifold, right? And then we keep building our database that way. And yep, so back to the key takeaways. So I think that there are 3 main things that, always compete when we want to build a neural network or ML surrogate. Is the accuracy, cost, and explainabilities. We cannot always, achieve all of them at the same time. Right? Sometimes it's just a trade-off between accuracy and cost, or between accuracy and explainabilities, or sometimes it's just a trade-off among 3 of them. So at the end, I just feel like sometimes it's, more art than science to actually find the compromise among these 3 to actually use in the real world applications. But yeah, thank you. That would be the end.
Great. Thank you so much for the presentation. We're opening up for questions, so please feel free to unmute and ask away.
I have a question, maybe I can start. For the first part of the presentation, you mentioned about the sampling and just taking 5,000 samples instead of 1.8 million samples that you have from the degrees of freedom. How did you do the sampling? How do you make sure that you get the right samples for the training?
That's a great question. So actually in the paper we show that, regardless, we try a couple, right? Like Latin hypercube, Sobol, or just randomly sample, or even do like a smart sample, like we kind of do the weights, right? Like so we weights the degree of freedom that have higher errors more. So we try a range of sample strategies, but we actually show that, if you do it long enough, like let's say 1,000 epochs, it all actually converge to the same accuracy. So I think what take away from that paper is like, if you do it many times, finally just reach to the same point. As you can do a different sample here too, right? To find the sample estimate. But if you do it a lot of time, you just reach to the same answer or the population mean. So yeah, that would be the takeaway that we found there.
So it doesn't really matter how you get your samples or from which part of the domain you gather your samples.
Yep.
Okay.
Yeah, we also try like, the higher gradients, of the saturation will have higher weights of the sample. They all just converge to the same thing. Yeah, kind of surprise you.
What else?
May I ask a quick question? So in the second part of your talk, you mentioned you had finite differencing to impose the. Yeah, I didn't quite understand that slide. I was wondering if you could explain that again.
You mean this one?
Yeah, the slide before.
The slide before. Yep. So at the last layer to predict, let's say we predict pressure or any state variable we actually apply a filter based on finite element stencil to that state variable to calculate the residue loss of any PDE that we enforce here, right? And in this case, it's just Poisson equation. So we know all the, del U by del X, del U by del Y, and also second derivative, right? We just apply the filter as an additional layer to the predicted output or U here. Yeah, it's very simple actually.
So then you obtain the I guess the residual.
Yeah.
Then what do you do with that?
And then like what that two way, right? One way we can just use that residue as a part of the loss function to optimize the all the trainable parameters here. But we also test the other way, right? To use the numerical integration in the red box here.
So you're just simply replacing the automatic differentiation of pin with your own finite differencing.
Yep.
Okay, thank you.
If you go to slide 18 where you compare the convergence plots, so
Yeah.
what do you think is the reason that the pin is not even worse than pure data-driven approach in this example? How do you interpret this?
I think there are a couple of studies that point out, right? That's like by just enforce the strong form of the pin itself without giving any data points inside the domain, right? So imagine you only enforce the boundary conditions, and then within the computational domain, you use only residue loss. Pin is very unstable. So people were proposing, some of the groups that like you should give some sample within the computational domain itself to make pin more stable. But by doing the weak form, right? we actually, instead of like strongly force each point in the domain to honor the governing equation, we kind of do the average, right? So the training is more stable. I think that's what we speculate at that point. Yep. That's why it's getting much better and more stable to train compared to the traditional pin loss or the strong form loss.
Is the majority of the error due to the boundary condition satisfaction, or it is due to some other reasons?
I would say that we exclude the boundary condition here, just within the domain itself that show the loss here. Yep.
Okay.
So my question is about the first half, sorry, the first part of the talk, more specifically when you introduced the graph neural network. So I mean, I'm completely new to like machine learning, so please bear me if it's maybe a naive question. So is the idea to incorporate the graph neural network is to kind of like, kind of incorporate information about how the nodes or like the discretization is connected to each other? And then so going back to the sampling idea, so I guess sampling means that you don't have like, all the information on all of the nodes, you only have like a subset. So how does that affect the whole connectivity information? How do you build that in when the sampling changes, like which point you're sampling from?
Oh, that's a great question. I love it. Yeah, I think you point out very great point. That's like we speculated that at that time why we went into graph, right? Because instead of represent these sample points using not a deep, right, but like multiple layers of neural network, we're thinking that by using graph, right, not only we aggregate, let's say how many points here, 5 points at a time, right? We also aggregate 5 time number of its neighbor itself, so it would reduce the number of layers significantly. So finally, we use only one message passing of graph, and it actually achieve a better accuracy than a deeper neural network, right? Because it just aggregate more points at the same time. And I think to your second question, how to create or how you find the neighbors, right? There are definitely 2 main ways. Like one, you can say fixed number of neighbors find the closest 4 neighbors, let's say. So you just you have the distance of all the points, right, and all the neighbors around it. You can just do top k and then you pick top 4 as the neighbors. Or you can also do that like with the radius of x, all the node that gather within this x, right, would be a neighbor itself. But that also that there are pros and cons, right? The first approach, you kind of fix that each node will definitely have neighbors. But for the second approach, you can imagine like, let's say you have a mesh that certain part of the mesh is very refined, right, and certain part is very coarsening. So if you fix number, fix radius, sometimes that node that's in the coarsen part, right, will have no neighbor at all. So that's one thing to consider to which way to construct neighbor of your graph itself. Yep, thank you. Is that answering your question?
Yeah, that sounds good. I should read your paper to learn more, definitely.
So the graph matches the topology of the mesh that you use to.
Yep.
I also have a question. So sorry, so comparing to deep nets, I guess in the original formulation of deep nets for the branch nets or the parameter nets or parameter embedded here, we assume that the location of these, I think they call it sensor points. The location of those sensor points should be fixed during the training and during the inference. But I guess with graph neural networks, is it becoming like sort of mesh free? So it doesn't, so the location of those sensor points can change, or is it still similar to deep nets where the location of those sensor points should still be fixed and the same for training and for inference?
I would say in the traditional deep net, at first I thought it had to be fixed, right? But from what I've been talking to those group of people for some time, and actually that there is no assumption that it need to be fixed to begin with. And here also, it doesn't need to be fixed, right? But also add additional point to that. Let's say you have, 10,000 sensor point. You don't have to use 10,000 points at the time. You can also use just, a subsample of those points per back propagation, which make your model more like generalizable and also cheaper to train. So yeah, that's a whole exercise in that paper, in this paper here. So your sensor point is still there, but you don't need to use all of them at the same time, and you can also move them around if you wish.
Thank you.
Thank you.